Hello everyone, my name is Lupita Gonzalez and today I'm going to be presenting my molecular portfolio on the drug Coumadin. A general description of my drug. So brand names include Coumadin, warfarin, and Jantoven. Generic names include Anismol and Aldokumar. The chemical name is sodium 4-oxo-3, 3-oxo-1-phenylbutyl chromin 2-olate. So what exactly is Coumadin, you may ask? Well, Coumadin is an anticoagulant medication. Anti means against, and coagulant means causing blood clotting. So if you put the word together, the drug is used as a blood thinner and can treat and prevent blood clots. You shouldn't take this drug when you have uncontrolled bleeding, open wounds, severe liver problems, or kidney disease. Significant interactions with other drugs would be with antibiotics like Avelox, thyroid, heart, or seizure medications. Interesting facts about Coumadin. Did you know that there are specific foods and beverages that will affect the blood thinning of Coumadin? Examples include alcohol, cranberry juice, chickpeas, spinach, pork liver, and green tea. So now I'm going to paint out my line bond structure. So you guys don't have to sit through this. I'm going to speed it up through time lapse and then I will explain it. Here's my beautiful structure and I hope you guys enjoyed my little time lapse. This is Coumadin. The main thing to know is that all carbons need to have 4 bonds, which is why some of mine are double bonded. Oxygens need to have octet, which is why we add lone pairs to them, so they have a full octet to be more stable. So now I'm going to be moving on to the expanded structure formula of Coumadin. So this is my structure, and as you know, the expanded structure formula shows all bonds connecting all the atoms in the compound. So, in this case, we know that ends and bends are carbons, and from there you add hydrogens, and then you add your oxygens and your lone pairs. So this is my structure. On the next page is the VSEPR theory molecular geometry predictions, and what you are looking at right now is my expanded structure that's also color-coded with the different bond angles. So, for instance, the purple is tetrahedral, and I have 4 bonds. The blue is trigonal planar and I have 3 bonds, and the lime green is bent and I have 2 bonds. Overall, the VSEPR theory isn't that bad, you just have to know the different bond angles and what they add up to. So, from what we know, the tetrahedral adds up to 109 degrees and the trigonal planar adds up to 120 degrees. It's pretty easy to identify once you get the hang of it. This was probably the easiest part for me out of all the molecular portfolio. So, to start, you have to know your molecular formula. So to find this, I went on PubChem and then it should have popped up. So mine was C19H16O4. And then from there, you have to find your molecular mass. So you take your carbon equals 19 times 12.0 grams equals 228.19. And then you would do the same for your hydrogen. So 16 times 1.001 grams equals 16.016. And then you would do the same for your oxygen. So 4 times 18 grams equals 72. And then from there, you would add all these numbers up to get your molar mass. So the molar mass of Coumadin is 316.206. This is the page that everyone had to do with the hydrogen bonding with water exercise, so I'm not really going to spend much time on it. I'm going to explain it more with my molecule, but as long as you follow the hydrogen bonding rules, this should be pretty easy. This is the hydrogen bonding with water, and what you are looking at right now is my expanded structure of Coumadin. And from here, we know that nitrogen, oxygen, and fluorine all form hydrogen bonds. So generally, they act as acceptors because they accept the hydrogen from water molecule during hydrogen bond formation. But if oxygen and nitrogen have a hydrogen bonded to them, they can act as a hydrogen donor because the hydrogen can be donated to the water molecule during the formation of the hydrogen bond. So in my case, I have 4 of them. One right here, one right here, one right here, and one right here. Polarity and solubility predictions. We were instructed to draw our molecule and then circle or highlight all polar portions of the molecule. So, in my case, I highlighted all the CO bonds because they are polar. And then we were instructed to make a reasonable prediction of whether or not our molecule would be soluble in water, and then explain. So, at first I thought mine was, but then I quickly figured out that I was wrong. because nonpolar molecules can only dissolve in nonpolar solutions. Therefore, my molecule would not dissolve in water. Although, because my molecule has CO bonds, it could be slightly soluble due to the carbon and oxygen bonds. But I came to the conclusion that Coumadin is a nonpolar molecule and doesn't dissolve in water. Finally, the last page of the molecular portfolio. These are the solution calculations. So in number 1, we were asked to prepare a certain amount of our solution. So in my case, it was Coumadin. So in my calculations, I did 50 milliliters times 1 liter over 1,000 milliliters times 2.3 times 10 to the negative second moles over liters times the molar mass of my drug, which is 316.206 grams over 1 mole, and then it got 0.36 grams. And then for number 2, we had to calculate how many milligrams of the drug are contained in a 2.0 milliliter of a 3.0% solution of our drug. So I did 3 grams over 100 milliliters times 2 milliliters, and then I did 6 over 100, and I got 0.06, which equals 60 milligrams of solution. And that's the end of my molecular portfolio. I hope you all enjoyed learning more about my drug Coumadin. I just wanted to say that I'm very proud of everyone that did this and went through this class. We literally went through so much together, and I couldn't be prouder of everyone.